In this calculator tutorial, we will learn how to perform linear regression on a TI-84. The first thing that we need to do is enter the data. For this problem, I will be using the minutes walked and calories burned problem from the Unit 1 notes. To enter data, you will go to the Stat button, which is near the arrows, and we're going to press Edit. You'll actually be in the Stat menu twice, once to edit and once to calculate. From here, you'll bring up a series of tables. We will be putting our data into L1 and L2, list 1 and 2. If there is already information in there, you can type over top of it. You can hit delete while you are on the number, or you can arrow to the heading L1 and hit clear. Don't hit delete while L1 is highlighted, or the whole column will disappear. We can help you reset that if you accidentally do that. Hit clear, enter, and all the data in L1 is eliminated. And we can do the same thing for L2. So we have blank list for inserting our set of data. In L1, we are going to put the numbers that correspond to the inputs, which is minutes walked. Type the first data piece, which is 1, hit enter, and continue typing in the remaining pieces of input data. In our problem, we have 5 pieces of input data, which means we should have 5 pieces of output data. Match them up with their input. And be sure when you finish that each input has an assigned output, or you will end up with a dimension mismatch, meaning one column has more data in it than another. Okay, you can go ahead and quit out of here. Second mode will quit, and the data is stored there until you delete it or type over it with something else. Now, suppose I hit the graph button to see what that looks like. I don't see much. The reason being is my calculator is set to the default window of x equals -10 to x equals +10 and y equals -10 to y equals +10. I'm going to go to my window and choose a better viewing window for this particular data. My input values are between 1 and 16, so I'm going to adjust the minimum. I'm going to use -2, and then for my maximum, I need to include numbers that are larger than 16, so I'm going to go up to 20. I don't care to change my X scale, but you can if you want to. And then the Y minimums, I have no negative values. I'll leave room for a couple negatives. I tend to leave a few negatives on here, even if I don't need them, because I like to see the X and Y axis and not have those be the edge of my screen. The maximum calories burned on our data set was 70. We'll choose a Y value that's larger than 70. And now if I hit graph, I should see all of my values. And again, I don't. The reason being is my calculator is set right now to graph whatever is in Y equals. And you can see that we don't have anything typed into Y equals. Above Y equals on my calculator in the top left, there is something called stat plot. And I'm going to turn that on so my calculator knows that I am graphing individual data points rather than a function typed into Y equals. Second Y equals, and I'm going to go into plot 1, and I'm going to turn it on. And if you notice on the type line, it shows scatter plot and then some other things that you might recognize from introductory statistics that you've done. In our X, it says L1 and L2. That's where our data is stored. If you don't like the little boxes, you could change it to the plus sign or the big dot. Either way, we need to turn the data plot on. Now when I hit graph, I see my 5 values, and I can see that it looks like the same thing that has been shown on my paper. And I can see that it's pretty linear, but not perfectly linear because it doesn't have a constant rate of change. Now we're going to go ask our calculator to make a line of best fit. And the calculator has access to all the data points and will run all of the background work in order to create the ideal equation for us to use. So we'll return to the stat menu one more time. And this time we're going to choose calculate. And you'll be in this menu multiple times this year. because we will fit curves to other sets of data besides just lines. And if you look at items 4 through 9 and so on, these are all the same task applied to a different type of function. We see a line. So we are going to choose item 4, which is called linear regression. And your calculator may look similar to mine. It may look slightly different, but we're going to hit enter until we see an equation pop up. And this tells me then it created an equation in the form y equals ax plus b, or slope-intercept, where the slope is 4.26. We'll round to the 100th here. And the intercept is 1.76. And we can see that that's pretty close to what we created on part B when we did things ourselves. So now we would write this equation on part C. Go ahead and round to the 100th. We will interpret our slope. Remember, the slope involves two variables. So we might say something like, as the minutes increase by 1, the number of calories burned increases by 4.26, or 4.26 calories are burned per 1 minute. Now, on E, it asks us about the correlation, and I don't see anything about this R variable that it's talking about. Your calculator may show that. It depends on if you're using a brand new calculator or not. Mine does not. This is a one-type thing. Let's go down to where it says 0. Above that, it says catalog. Your calculator defaults to not having the diagnostics on. So we are going to turn it on, go to second catalog, and we're going to scroll down until we find something called diagnostics on. Okay, here we go. So we're going to turn diagnostics on. And again, you only have to do this once, or if you end up resetting the memory on your calculator, you would have to do this again. And we'll hit enter, so it is now on. We're going to go back and do the stat calc linear regression one more time, and you'll see the difference when the diagnostics are on. Now I get two more pieces of information. We will ignore the R-squared value. That is something that you will use in a formal statistics class, but we will reference the R value of 0.999935. And what that tells us is that this problem, since the R value is very, very close to 1, that this is a very, very good fit for the data. Perfect correlation means R equals 1 or R equals -1 in the data where you have decreasing values of Y as X increases. Our example was positive correlation because as X increases, so does Y. So we could judge this number and compare it to 1 or -1 to assess how strongly the data is modeled by our equation. So in this case, we would list R equals point. I'd probably go out to maybe 4 decimal places to show that its relationship with 1. And then we would say that this is a positive correlation, and I would assign it a very strong value. Now, if we came up with R equals 0.75, then we would see some points that are not as closely mirrored by the line, and you would change your judgment. It's still positive, but it's not as strong. And it depends on what you're trying to communicate. If this is medical data, then maybe you wouldn't accept a correlation of 0.5. In our case, we can see that our value is very strong. It's very close to 1. And then this will be here from now on when you calculate linear regression, because that diagnostics will remain on unless you turn it off or reset your calculator. Now what we can do then is proceed as usual. We have our equation, y equals 4.26x plus 1.76. We can now go back to y equals, and we can type in the equation for this particular data set. and we can use it to make predictions about other things. The whole reason for creating a line of best fit is to use it to make predictions for other things. What happens if I walk for 30 minutes? What would I need to do in order to burn 80 calories? So we would want to use this equation to answer any other question. Now, your calculator doesn't like the scatter plot to be on at the same time as a function is being graphed. So since I'm done with the scatter plot, I'm going to go in and turn that off, go back into plot 1 and select off. And then now when I go back to y equals, I can tell that it's off because plot 1 is not highlighted. And now when I graph, I can see my equation. You can still graph it while the points are turned on. It's kind of rewarding to see it pass through a lot of those. But if you're going to do calculations like we are getting ready to do, then we don't want that scatter plot turned on at the same time. And sometimes that's the reason for getting error messages later is students forget that their scatter plot is turned on when they are trying to do things that have nothing to do with the scatter plot. So on part F, it says what would happen if I walk for 30 minutes. Well, I could input my value of 30. I want to make sure that my window goes out to include a value of 30. So I'll consider what would happen if I walk for 50 minutes. And then I can say trace 30 minutes. And I can see that I burn almost 130 calories for 30 minutes of walking. Remember, you could also look that value up in the table by hitting second graph and scrolling through the table until you find the value that matches up with 30 minutes. On part G, it asks us to use our equation in order to find an equivalent number of minutes walked when 150 calories are in a serving size of Cheez-Its. So I'm going to go to my window for Y, and my Y max is now set at 80, and remember that's 80 calories. So I'm going to increase that to 200. And I can see 50 minutes of exercise being graphed and up to 200 calories being burned. And I'm going to force my calculator to answer this question for me. I'm going to type in Y equals 150 calories. And I'll graph both of those and I can see where they intersect. That is the number of minutes I'm interested in to know what it would take in order to burn or match up to 150 calories. And I can pull up the calculate tool, second trace, and choose intersect. And my calculator prompts me to select the blue line, or the Y1 equals 4.26x plus 1.76. Hit enter. And then I'll do the same thing for Y equals 150. And then guess the intersection to be 34.8 minutes to burn 150 calories. I could also do this part by hand. I could set the 150 equal to the 4.26x plus 1.76 and solve by hand. But once you create the equation, you can complete the entire process on your calculator as well. Just a note while we're in here, as you move forward and complete the next problem, a nice little trick is to hit zoom 6, and your calculator will go back to a 10 by 10 window if you want to remove all of the window restrictions that you set on the previous problem. It's always nice, I think, to start from the standard 10 by 10 window.